Hello friends, welcome to our channel. I hope you are all in a very good health and doing well with your studies. Thank you for joining me. Today we are going to discuss some important topics from refraction of light. In our previous class, we have discussed up to laws of refraction and refractive index. Today we are going to define absolute refractive index. Absolute RI, absolute refractive index. So, absolute refractive index of a medium can be defined as the ratio of speed of light in vacuum to the speed of light in that medium. For mu is so speed of light in vacuum can be represented by small c, and speed of light in that medium can be represented by v. So this is our refractive index or absolute refractive index of a medium. Here we can see the speed of light in vacuum is maximum. So this ratio is always greater than 1. as the speed of light in vacuum is maximum. So it cannot be less than 1. So refractive index of second medium with respect to the first medium can also be written as we know this can be written as sin I by sin r, but this thing can also be written as v1 by v2. That means speed of light in medium 1 by speed of light in medium 2. Okay. This thing, that means refractive index of medium 2 with respect to medium 1, can be written as v1 by v2, where v1 is the speed of light in medium 1, v2 is the speed of light in medium 2. This thing can also be written as c by v2 by c by v1, which is actually this thing. See the numerator is actually the absolute refractive index of medium 2, and this is the absolute refractive index of medium 1. So mu2 1 can be written as v1 by v2, which can again be written as c by v2 by c by v1, which is actually absolute refractive index of medium 2 by absolute refractive index of medium 1. So this format and this format is important for our numericals. Again, we can say that mu2 1 can be written as v1 by v2, and we know speed is actually frequency into wavelength. Speed v is equal to frequency f into wavelength lambda. So v equal to f lambda. So we can write in place of v1 f lambda 1 by, in place of v2 we can also write f into lambda 2. Here we can see we are using this relation V equal to f lambda. Okay, we are substituting f into lambda 1 in place of v1 and f into lambda 2 in place of v2. So this is what we are getting, and we can see the frequency remains same in both of these media. Frequency does not change when light goes from one medium to another. Frequency remains same. Frequency depends on the source of light. Okay, frequency only depends on the source of light. It does not depend on the medium through which the light is traveling. So, and this is f lambda 1 and this is f lambda 2. So f and f can be cancelled. So we can write lambda 1 by lambda 2. Okay, so refractive index of second medium with respect to first medium can also be written as this, lambda 1 by lambda 2. That means wavelength of light in medium 1 by wavelength of light in medium 2. So when light changes from when light goes from one medium to the other, we observe a change in speed. So the change in speed occurs due to the change in wavelength. Okay, so when speed changes, frequency remains same. So we can say when speed changes, wavelength also changes. So when light goes from one medium to the other, its wavelength changes. So mu2 1 can be written as lambda 1 by lambda 2. This is another important way of writing refractive index of medium 2 with respect to medium 1. Okay, so these three formats are important. You need to remember these things. Now let us discuss about the factors affecting the refractive index of a medium. Number 1, nature of the medium. Nature of the medium, that means if the optical density means which determines the speed of light in that medium. Okay, or we can say optical density or the speed of light in that medium, if it increases, if optical density increases, if the optical density increases, the speed of light in that medium decreases. And when speed of light in that medium decreases, the refractive index increases. So if the optical density of the medium increases, upward arrow, that means it is increasing. Okay, if the optical density increases, the speed of light in that medium decreases. Downward arrow means it is decreasing. Okay, the speed of light in that medium decreases. When speed of light in that medium decreases, its refractive index increases. And when the optical density decreases, downward arrow means decreasing. Okay, when the optical density of that medium decreases, speed of light in that medium increases. And when speed of light increases, refractive index decreases. Okay, now come to the next point. Temperature. As the temperature of the medium increases, speed of light also increases. Therefore, the refractive index decreases. Okay, so when we increase the temperature of a medium, the speed of light in that medium increases. And when speed of light increases, refractive index of that medium decreases. So refractive index is inversely related to the temperature. Now let us come to the third point. Color or wavelength of light. For a specific medium, the speed of red light is maximum and the speed of violet light is minimum. Therefore, the refractive index of that medium is maximum for violet light. As the speed of violet light is minimum, therefore we can say the refractive index of that medium is maximum for violet light and minimum for red light. Okay, we can say that when the wavelength increases, refractive index decreases. So we can see that when wavelength increases, the refractive index decreases. The wavelength of red light is maximum, that is why it's that is why the refractive index with respect to red light is minimum. So wavelength and refractive index are oppositely related. Now we are going to learn about lateral displacement. Let us assume we have a rectangular glass block. This is our rectangular glass block. Let us name it ABCD. And let us assume this is air, this is glass. So the glass block is placed in air and a light ray is coming through air and which strikes the rectangular glass block obliquely. So this is our incident ray. Let us draw our perpendicular at the point of incidence. This is our perpendicular and let us assume this is O. So when the light ray strikes the glass block, as it is traveling from a rarer to a denser medium, it bends towards the normal like this, and it again strikes the other side of the glass block. Let us draw another normal. Let us name it N dashed, M dashed. Now the light ray again enters air. So as it is traveling from a denser to a rarer medium, it bends away from the normal. This is our incident ray. This is refracted ray, and this is emergent ray. Now we can see that the light ray, in the absence of this rectangular glass block, the light ray should be following this path. But when we place a glass block in its path, it gets refracted two times, and the emergent ray becomes parallel to the incident ray. Emergent ray is parallel to the incident ray, and it is laterally displaced. It is laterally displaced. This phenomenon is called lateral displacement. Now this is our angle of incidence. This is our angle of refraction. I hope it is clearly visible. And as faces, these two faces are parallel, and this is our transversal. So this angle is so these two angles are alternate angles. Okay, two parallel lines, one transversal. So this angle and this angle are alternate angles. So alternate angles are equal. That means this angle is also R. Okay, and this is our angle of emergence. According to principle of reversibility of light, angle I is equal to angle E. That means angle of incidence will be equal to angle of emergence. Principle of reversibility of light says when we send a light ray from one medium to another medium, something like this. When we send a light ray from one medium to another medium, it gets refracted. So let us assume this is our rarer, this is our denser. So when we send this light ray from the first to second medium, it bends towards the normal. So when we send light ray from the first medium to the second medium, this is our first medium, this is our second medium. The path followed by light will be exactly equal to the path when the light is sent backwards. That means if we send light from first to second medium, and if the light ray follows this path after refraction, the same path will be followed if we now send the light ray from second medium to the first medium in opposite direction. That means now we are sending from second medium to the first medium. Okay, the direction is reversed. The light ray, when sent in opposite path after refraction, it will follow the previous path. Okay, so it does not matter in which direction we are sending the light ray. Okay, if we send it from first to second medium, the path followed by it will be exactly same if we send it from second to first medium. Okay, this is what the principle of reversibility of light says. In forward and backward direction, the light ray follows the same path. So according to the principle of reversibility of light, the angle of incidence will be exactly equal to angle of emergence. Now this distance the perpendicular distance between the emergent ray and the incident ray when it is produced forward This distance is called lateral displacement. So let us denote it by x. This is called lateral displacement. So let us determine the value of x. Let us do one thing. Let us draw a line, a perpendicular from this point on the let us draw a perpendicular on the dotted line from this point P. So this is our perpendicular. So if this distance is x, this distance is also x. Okay. Let us name it PQ. So we are observing a right angle triangle OPQ. Now let us do one thing. Let us produce NM to meet the side DC. Let us name it R. Okay. So we are producing, we are dragging the line, the perpendicular NM to meet the line DC. Okay, this is a perpendicular. So we are getting another right angle triangle ORP. So now we have two right angle triangles PQO and ORP. So we can write we have very little space. Let me write it as clearly as possible. In our first right angle triangle, triangle OPQ, triangle OPQ, in triangle OPQ, we can say this angle, see carefully, this angle is, the total angle is angle I, okay, because it is vertically opposite. So the total angle is angle I, but this part is angle R. So this angle will be equal to angle I minus R. See carefully. This angle and the total angle are vertically opposite, so they are equal. So the total angle is equal to I, but this part is R, so this part is I minus R. So this angle is I minus R. So we can write sin I minus R is equal to PQ by OP. Okay, perpendicular by hypotenuse. PQ by OP. So PQ is equal to X and it is OP. Now in triangle ORP, this is also a right angle triangle. ORP, we can write cos of angle R, cos of angle R is equal to base, that means OR. Okay, this is the base, the dotted line, by hypotenuse OP. Okay, so the base is equal to the thickness of this glass. This is our thickness T. So let us represent the thickness by small t. So OR is equal to small t by OP. Now in place of OP we can put, okay, so let us write OP from this equation we can write or, okay, or we can write OP is taken to the left side, OP, and cos R is taken to the right side, so T by cos R. Okay, so this is the value of OP. Now we can put this value to the first equation. We are putting this value to the first equation. So we are getting sin I minus R is equal to X by, in place of OP we can write T by cos R. Now if we transfer this quantity to the left side, we get T into sin I minus R by cos R is equal to X. So this is the value of lateral displacement. If we know the value of thickness of the glass slab and angle of incidence and angle of refraction, we can easily find out the value of lateral displacement. So this is our equation. Now let us come to the next point. Lateral displacement depends on factors such as thickness of the block, more the thickness, if the thickness of the block increases, lateral displacement will also increase. Number 2, the angle of incidence. If the angle of incidence increases, lateral displacement will also increase. Refractive index of the medium. If the refractive index increases, lateral displacement also increases. Okay, so I hope this is clear to you. Lateral displacement depends on these three factors. Now, let us come to the next point. Multiple images by thick mirror. Let us assume we have a thick mirror. So this surface is silvered. This is the reflecting surface. Okay. So this is the thickness of the mirror. Now let us assume, an illuminated object. Okay, an illuminated object is placed in front of this mirror. Now let us draw a perpendicular line. So this is our object O. So the light ray from it coming towards the mirror, and it enters the first surface of the mirror without suffering any deviation, because it strikes the mirror perpendicularly. So the light ray enters directly without any deviation, and after that it strikes the second surface of the mirror. This is the silvered surface. So it gets reflected. So the ray coming perpendicularly gets reflected back following the same path, but in the opposite direction. And let us assume another ray which is coming obliquely, strikes the mirror, and it gets refracted. So this is the refraction, and again the refracted ray gets reflected by the silvered surface. So this is something like this. Again the ray gets again we can see that when the light ray strikes the first surface obliquely, a part of this ray enters the glass slab. Okay, and another part gets reflected. Again, the refracted ray strikes the second surface and gets reflected back. And when it hits the first surface, a part of it gets refracted. And the other part of it gets reflected. So the process continues. So in this process, if we keep our eye somewhere like this, we can see multiple images. This is the first image, I1. This is the second image, I2. This is the third image, I3. This is the fourth image, I4, and so on. So in this process, out of these images, the second image will be the brightest. I2 is the brightest image. And as we go downwards, the intensity of the images will keep on decreasing. Okay, so when the light ray comes obliquely, only we can say nearly 4% is reflected in this direction. Okay, in this direction. So this is nearly 4%, and the 96% is refracted. And this ray, after striking the second surface, gets reflected, and when it gets reflected, most of this energy, most of this 96% energy, most energy gets refracted, and a small part of this energy gets reflected. So the intensity of the second image is the most. If we put our eye in front of this mirror, and if we see obliquely, we shall see many images inside the mirror. Okay, we can see multiple images. I hope it is very clear to you. That's all for today. Thank you, friends.